Hey everyone, and welcome back to our electronics tutorial series. My name is Aaron from AX Electronic, and today we are going to expand on the topic of MOSFETs as switches and start talking about MOSFET logic. So, those of you who are familiar with digital logic might know that using just switches, you can actually perform a lot of basic logic operations. And then using those basic logic operations, you can expand them into cool things that can do maybe lots of cool math, like addition, subtraction, multiplication, things like that. You can also expand them to maybe even artificial intelligence in the very, very long run, okay? So you're not going to be able to use just these simple circuits for any sort of artificial intelligence, but you can make some basic decisions using these MOSFETs as switches. So we're going to go ahead and jump right into it. So logic. First thing I want to do is define what logic is, just in case you're not familiar. So logic in this sense is a set of rules that form the basis of performing mathematical operations in an electronic circuit. So if you have something like an Arduino, you might be wondering, how does it add two numbers up? Or even a more basic microcontroller that doesn't have all the stuff the Arduino has. How does it perform all this math and get it correct every single time? And the answer is that it uses logic circuits in order to accomplish that. So logic circuits are actually a very big application of MOSFETs because they offer a lot of good advantages that we'll talk about. So what we want from these logic circuits is that we want them to change their output based on some rules that we set. So we're going to set some rules, and then we want it to change its output based on the inputs and those rules. So these are called logic gates, and these are the fundamental logic operations, and we'll review those right now. So this symbol here, which is like a D with three terminals. This is in, and out. This is an AND gate, okay? And we'll talk about it here in a moment. So for this one down here, this is OR. So we have an in, and out. We also have this one, which is an inverter, or NOT. And we only have one input and one output. And this is an example of a what's called a NAND gate. And there's definitely more logic gates that we'll talk about. And I'll review them before, but it also has two inputs and an output. Okay, so let's do a little bit of a logic review. So let's start with the simplest case possible, the inverter or the NOT gate. So what it does is it does exactly what it sounds like. So it's going to invert whatever signal it gets. So for this video, I'm going to use ones and zeros. So this is going to be on, zero is going to be off. But for many applications, if you want to maybe draw it back to the electronics or the switches we've been talking about, you could consider on as our 5 volts or 3.3 volts or whatever our high level voltage is, and off could be 0 volts. Okay, so that's just to make sure that we are all on the same page. So ones and zeros are what we're dealing with today. So like we said, we have one input and one output. So let's say that our input is 0. Okay, so what we want this inverter to do is that we want it to flip that 0. So we want it to flip this one single bit. And to do that, it's going to output a 1. So it's going to take this input 0 and it's going to output a 1, or that on signal, or 5 volts. Same thing, if we get a 1 on the input, we want it to flip and output a 0. Okay? So this is a pretty simple logic operation that all it's doing is just flipping. So it's inverting. You can also think of it as saying not the input. So if our input is high, we want it to be not high on the output, or we want it to be low or 0. So the next thing that we can build on is the AND gate. So remember, this is the AND gate. It looks like a D with 2 inputs and 1 output. You could have whatever number of inputs that you want. It does not matter at all. You could have 10 inputs, 8 inputs, stuff like that. So these are both inputs, and this is our output. So I'm going to call this one input A, and this one input B. Doesn't matter though. You could flip them and it would be the exact same result, okay? This is our output on this side. So what the AND gate does is that it's going to return a high signal if input A and input B are both high. So this is saying both of these conditions have to be true. So A and B has to be high for the output to be high. So let's look at the first case. So if we look at the case where they are both low. So they are both low. That means input A and input B, neither of them are high. Okay, so if neither of them are high, that means we are going to get a 0 or a low on the output. So now let's say that our input A is still 0 and our input B is high now. So ask yourself, is A and B both high? And the answer is obviously no, because A is still low. So they are not both high. So we're still going to return 0 on our output. Let's try flipping this situation. So if we have input A high and input B low, is input A and B high? Again, the answer is no, because B is low, we're still going to output 0. And the only way that we are going to output high is if both input A and input B are both high. So this is our example of an AND gate. So it's going to only output a high level if A and B are both high. Okay, so we're just reviewing the logic. That way you can get a very familiar, or a brief familiarity with these operations. So I'm not going to talk as much about the applications of these logic circuits, but trust me, they are very broad and you can do a lot of cool stuff with these gates. So let's switch directions to an OR gate. So this one's a little bit different. It has these two inputs and kind of that curved and pointy area there and a single output. But just like the AND gate, you could have multiple outputs. You could have, or excuse me, you could have multiple inputs, 8, 10, 20, whatever it is that you want. So once again, we're going to call this one A and this one B. This is our output. Now what we want this OR gate to do is that we want it to output high if either A or B is high. So it doesn't care about them both being high, it just cares about one being high. So let's look at our first case. So if we have input A is 0 and input B is 0, is input A or B high? Neither one of them is. So our output is still going to be 0. Now, if input A is 0 and input B is high, now that statement is true. Input A or B is high. So just because input B is high, it's going to force the output to be high. Same thing if it's input A high, input B low. Input A is still high, so A or B is high. We're still high. Now, if input A is 1 and input B is also 1, A or B, they're both high, so we can still output a 1. So that is our OR gate. Now, NAND is a little bit different. So NAND is short for not AND. And pretty much all it is that it is an AND gate. Okay, so it's an AND gate followed by an inverter. Okay, so we're going to take the output of this AND gate and invert it. So if you remember, our inverter just flips whatever the output is. And our AND gate has this truth table here. These are called truth tables because this is telling us what's true. So if this is high, or if our output is high, then we're saying that our statement is true. So if we consider just an AND gate and an inverter, we can draw up this truth table very easily. And the way that we represent a NAND gate is that we just have an AND gate with this little dot at the end. So usually that dot's going to tell us that the output is flipped, or that it's active low. So once again, we're going to have input A and input B into this NAND gate. So our first case, if they are both low, so if input A is low and input B is also low, then our AND gate is going to output 0. But if our AND gate outputs 0 and it's inverted, our actual output is going to be 1. Okay, so we can continue filling this in a little bit quicker. So in this case, is A and B high? Answer is no, but then our output is inverted, so it's also a 1. Now, once again, that's not what we need here. If I do 1 and 0, is A and B high? No, but our output's inverted, so we get a 1 again. And for our last case, is A and B high? This time, yes, A and B are both high. So our output should be a 1, but then it becomes inverted. So now it is a 0. Okay, so now we have a 0. So you can see that this NAND gate is the exact same as our AND gate followed by an inverter. So it's just the flipped output of, it's just the flipped output of an AND gate, or a not AND gate. Alrighty. So if there's a NAND, then that means that there must also be a NOR. So we saw our inputs A and B. B. We have our output here. And if our NAND was just an AND followed by an inverter, then you know this one is just going to be an OR followed by an inverter. So it's going to take whatever our OR gate output was and flip it. Okay, so we can run through this one a little bit quicker now. So if we have input A is 0 and input B is 0, is A or B high? No, but then it becomes flipped. So our output is now high, right? Because before our output was 0, now it is 1. And then for all the rest of these cases, if either one of them is high, our output is going to be low. Because remember, this is our OR gate that we tackled before with its output flipped. So before, our truth table's output was 0, 1, 1, 1. Now it's 1, 0, 0, 0. So every single output has been flipped. So let's start looking at how we can implement these circuits with MOSFETs. So I'm going to give you some circuits, we're going to fill out its inputs, and then we're going to figure out what kind of logic gate this corresponds to, okay? So here, this is our input, and this is our output. Now, if our input is low, so let's say if our input is 0, okay, so if our input is 0, is any current going to flow through this MOSFET at all? Okay, so is any current going to flow at all? And the answer is no, because if our input is low, our VGS is going to be 0, and that means no current flows at all. So that means whatever this voltage is here, VDD, it's going to propagate directly to our output. So our VDD is our high signal level, so that means our output is going to be high. Now, if we flip this case, so if we say that our input is now high, so high is the same as VDD, that means that our MOSFET is now going to have a VGS equal to VDD, which could be something like 5 volts, 3.3 volts, and it's going to make this MOSFET start to conduct. Okay, so once this MOSFET starts to conduct, it's going to conduct a good amount of current, and it's going to conduct enough, in an ideal case, to drop the voltage across this resistor. Okay, so the majority of the voltage drop is going to be dropped across that resistor, and at our output, we're going to have a signal that is about 0 volts. So our output is going to be 0. So this is just a one input, one output device that flips the input. So which one is this? This is an inverter. Okay, so this is an inverter or a NOT gate. And its symbol is this right here. So this is a very basic example of an inverter and how we can implement this using a MOSFET. Okay? So let's try something a little bit more complicated now. So before we just had a single MOSFET, and now we're going to have two of them cascaded, one on top of the other, okay? So we're going to have two inputs now and one single output. Okay, so this is our A, and this is our B. Now, let's start off with the case of input A is 0 and input B is 0. So if input A is 0 and input B is 0, then that means that neither one of them is going to want to let current flow, right? Because both of their VGS is low. So neither one of them is going to want to let current flow. And whenever that happens, like we said before, there's no voltage drop across this resistor, so this voltage appears right on our output. So our output is 1. Now let's look at the case where input B is on and input A is off. Okay, so now input B is trying to conduct current, but input A says, or this MOSFET here says, I don't want to conduct any current at all. So this MOSFET is going to block that current from ever flowing. So even though this guy is trying to get current to flow really, really badly, this MOSFET B down here, MOSFET A is not going to let it happen. Okay, so we still get that same situation where there's no current flowing. So this voltage, there's no voltage drop across that resistor. That voltage appears on the output, so our output is still 1. Now, if input A is 1 and input B is 0, input A is going to try to get current to flow, but we don't have a path to ground because input B says, I don't want any current to flow. So no current is going to be able to flow through either of them. And that means that, again, our voltage appears on our output. Now, the different case is where they are both turned on. Okay, so they are both turned on, and whenever that happens, both of them are going to try and push current through them. And remember, these are acting like switches, so their voltage drop is really, really small. So even though there is a non-zero voltage here, it might be something like 0.01 volts. So this one is still turned on really, really well, and that means that our output here is going to be something almost 0 volts, because now we have current flowing through this resistor, meaning we have a voltage drop across this resistor, and now our output is going to be pretty much 0. So if both of them are high and both of those MOSFETs are conducting, they're agreeing to conduct, our output is now 0. So let's try and figure out which of those logic gates this configuration is. So we have 1, 1, 1, 0. Let's start at the very beginning. So we know it's not the inverter because the inverter only has one input and one output, and ours has two inputs and one output. So it's not the AND gate because the AND gate is 0, 0, 0, 1, and we need 1, 1, 1, 0. It's not the OR gate, although it's a little bit closer because we have 0, 1, 1, 1. Now, could it be the NAND gate? If we take a look at the output of this NAND gate, we see that the only way it's low is if both of the inputs are high, which is exactly what this case is here. So this is our NAND gate. NAND gate right here. So remember the symbol for this one is the AND gate, which looks like a D. Doesn't have that point at the end, although I didn't do a good job of showing you it doesn't have that point. So it looks like this D here. It has a little dot at the end of it, okay? So it's just an AND gate followed by an inversion, okay? Now one thing that you might notice is that this NAND gate is one of the simplest gates that we can make. So we only needed 2 of these N-channel MOSFETs in order to make this NAND gate. Okay, so we'll look at how this kind of changes in this slide here. So if we ignore this part here, if we don't look at this part at all for right now, what we can see is that in this section here, we already know what this is. So if we consider this our input A and this our input B, and this terminal right here is our output. This looks exactly like what we just found out is a NAND gate. So we know that this is exactly a NAND gate. So this section here is a NAND. Now let's take a look at this one on the right here. So this one we have a single input into the gate of our MOSFET here. So let's just call that A. And we have a single output. And if we take a look a couple of slides back, we can see that this is exactly our inverter. Okay, so this is an inverter or a NOT. So what we have is that we have an AND, or a NAND followed by a NOT. So we have the truth table for the NAND. So we know that if they're both 0, our NAND is going to output a 1. But if we output a 1 in this little middle section right here, then we're going to get a 0 on the output. So our output is now 0. And you can continue filling this in, and what you'll find is that the only way, oh, that's not the right way, the only way to get our output to go high is if both of them are 1s. So if both of them are 1s here, then we're going to have a 0 and a 1 on our output. So the only way to get this to go high is to make this, to make this both the inputs 1. So now we have turned a NAND and NOT gate into an AND gate. And this is a pretty interesting thing to know. So our NAND gate, remember, is the same thing as an AND followed by an inverter. Okay. Now, in this circuit, we have a NAND followed by another inverter. So that's the same thing as having an AND followed by the inverter, followed by a whole nother inverter here. So if you flip two things twice, or if you flip the output twice, that's pretty much going to cancel each other out. So these two are like they're not even there, and all we're left with is the AND gate. Okay, so that's just a little bit of a digital logic trick that you might want to remember whenever you're working with this stuff. So if you have a NAND gate, you can flip it and turn it into an AND gate using just an inverter. So let's look at this different configuration now. So let's look at this, a little bit different configuration. So now, instead of having these two MOSFETs cascaded, they're working in parallel. Okay, so they are working in parallel. Let's call this one A and this one B. Now, if input A and B are both 0, that means there's no current flowing here and no current flowing there. So no current is flowing at all into this MOSFET or this one here, and we're going to assume that there's no current flowing in the output. Now, what that tells us is that there is no path for any current to go through this resistor and go to ground. So that means there's no current flowing through that resistor at all. So our VDD is not going to drop. So our VDD does not drop, and that VDD appears right on the output. So if both of these are low, our output ends up being high. Now, let's say that we set B high and A is low. Okay? So now our B is high, and it's going to try and conduct current. So it's going to try and pull some current through here. A says, I still don't want to conduct. But A doesn't have any influence on B because they are working in parallel. So what happens is that now there is a path from VDD through the resistor and through this MOSFET here to ground. So now we will see a voltage drop across this resistor. And if this MOSFET is operating like a switch, then what we're going to see is that this output is going to be pretty much 0. So now our output has become 0. And because of the symmetry, the same thing happens if we have A turned on instead of B. So if B is refusing to draw any current, but A is okay with it, then we're going to see current through this resistor and through A to ground. So we're going to get that same drop and get 0 on the output. And finally, if B is also on and B is also conducting, then we're going to have two paths. So it's going to split here, and it's going to go through both of these transistors to ground. And we're still going to have a large voltage drop across that resistor, and we're going to get 0 on our output. So if they're both on, we get 0. So let's try and figure out which of these gates this corresponds to. So let's start from the beginning again. We know that it's not the inverter. We know that it's not AND because we have a 1, 0, 0, 0 in this new configuration, right? So 1, 0, 0, 0, that's what we need to remember. So we know it's not AND. We know it's not OR, right? Because we're starting off with the 1. It could be a NAND based on the first example because it's 1, but then we have a 1, 1, 0, or excuse me, a 1, 1, 1, 0. And we need a 1, 0, 0, 0. 0, 0, 0, that's right. So we can see that it is actually a NOR gate or a not OR gate. So that is exactly what this is. This is a NOR gate, which if you remember has a curve and a point at the end and a dot. And it's the same thing as an OR gate, which I'm trying to make that point very clear, followed by an inverter. Okay? Now, if we take a look at one more example, okay, so we can see that we have two sections here that we're going to try and separate. And usually, sectioning off your circuits can give you a pretty good idea of what's happening. So if we can section these off clean as inputs and outputs, then we can maybe make a little bit more sense out of it, okay? So we know what this is, right? This is our NOR. And we also know what this is because we've seen it a few times now. That's our NOT. So now what we have is an inverter, or excuse me, not an inverter, a NOR gate, followed by an inverter, which based on that rule that we saw a couple of slides back, we can separate that NOR into an OR, followed by an inverter. So this has become these two there. And then this is followed by a second inverter. And if you have two inversions right after each other, those cancel out. We know that this is going to end up being an OR gate. Okay, so this is what we're predicting for it to end up being, but let's still step through it and make sure that we're not crazy. Okay, so we have A, B, and our output. So if A is 0 and B is 0, these are both going to conduct current, so that means that this point here is going to be 0. And if we have 0 here, no current flows, so that means our output appears, or our VDD appears on our output, so we get a 1. Wait, that's not exactly correct. Okay. Let's step back a second. Okay, never mind. I messed up a little bit. So if we have both of these not conducting, yeah, I'm glad I caught that. So we have both of these not conducting. That means our output is going, or our VDD is going to appear here. So we're going to get a 1 here. And that's going to be inverted and become a 0. So now we have our 0 on our output. Now we're making more sense. Now, if either one of these starts conducting, so if it's 0, 1 or 1, 0, if either A or B starts to conduct, we're going to get a 0 on our middle output there. So this is going to be pretty much shorted to ground. We're going to get a 0 here. And if we have a 0, that means no current is flowing in this resistor for the inverter. We're going to have a 1 on our output. So both of these are going to give us a 1. And same thing if we have 1 and 1 on our input. Both of these are going to be pulling current. Still going to give us a 0 here, which is going to give us a 1 on the output. Boom, now we've made an OR gate, okay? So using these basic logic circuits like a NAND and a NOR, followed by an inverter, we can make all sorts of other different types of logic gates, okay? So I believe that that was all that I had for you guys. So this is a little bit of a brief introduction to logic, and now I understand that you may be a little bit more confused, maybe wondering why we're so concerned about these logic operations. Well, like I said, you can make a lot of really cool circuits using these digital logics, or using these digital logic operations, and or NAND, NOR, and inverters. So if you want to do a little bit more research on this, I suggest looking at digital logic basics. That way you can find out maybe how we can apply these to things like adders or decoders. If you do have questions for me, please feel free to leave them in the comment section below. If you like this content, please give me a thumbs up and subscribe to see more. It keeps me extremely motivated. And if you have, like I said, if you have any questions, leave them in the comment section below. Other than that, thank you guys for watching, and I will see you next time.